We hear about AI learning all the time, but what's actually going on inside that so-called digital brain? It's really not magic, I promise. It all comes down to three fundamental pillars. And today, we're going to tear them apart. We're talking loss, activations, and optimizers.
So how does an AI actually learn? It's probably the biggest question in tech right now. And the answer? It's not some crazy complicated black box. It's actually a really elegant and surprisingly simple loop, a process that literally turns mistakes into intelligence. All right, let's break this down. At its very heart, AI learning is basically a three-step dance. First, the model takes a shot. It makes a prediction. Then it looks at how wrong it was, and it's almost always wrong at first. And finally, it uses that feedback to tweak its own internal wiring, just a little, to make a better guess next time. And it does this over and over and over again, millions, sometimes even billions of times.
Okay, let's start with that first big piece of the puzzle. How does the model even know if its guess was good or bad in the first place? I mean, how do you even measure a mistake?
Well, that is the entire job of something called a loss function. The best way to think about it is like a scorecard, or maybe a grade on a test. For every single prediction the AI makes, the loss function gives it a score. And the goal is simple: get the lowest score possible. A high score means nope, bad guess, and a really low score means, hey, you're getting warmer.
And here's where it gets really interesting. How you decide to score the mistakes can completely change the way the AI learns. So let's say you're trying to predict a house price. You could use mean squared error, or MSE. This one squares the difference, which means it absolutely hammers the model for big mistakes. A prediction that's way off gets a massive penalty. But then you have mean absolute error, or MAE. It's a lot more chill. It doesn't freak out about huge errors, which makes it a fantastic choice if you know your data has a few weird, outlying prices that you don't want the model to obsess over.
So the main takeaway here is that you have to pick the right tool for the job. You wouldn't use a hammer to screw in a light bulb, right? Same idea. If you're predicting a number on a continuous scale, that's called regression, you'll grab a tool like MSE or MAE. But if you're trying to classify something into a bucket, like is this a cat or a dog, you need a totally different kind of scorecard, something like cross-entropy.
Okay, so the model has its score. It knows how badly it messed up. But what about the machinery that actually made the guess? How do all those millions of tiny little artificial neurons inside the network actually come together to make a decision? That's where the activation function comes in. Seriously, you can think of it as a tiny little bouncer or a gatekeeper at the door of every single neuron. It looks at the incoming signal and makes a simple choice. Is this important enough to let through to the next level? Without these little guys, the entire neural network would just collapse into a basic linear equation, which is, not very smart.
Now, you've got a few different kinds of these gatekeepers to choose from. The older ones, like Sigmoid and Tanh, they're kind of like dimmer switches. They smoothly adjust the signal, squeezing it into a specific range. But the undisputed rock star of the modern era is ReLU, and its genius is its simplicity. If the signal coming in is positive, it lets it through. If it's negative, it just shuts it off. Zero. It's a dead simple but incredibly powerful on-off switch.
So why is this simple on-off switch so dang popular? Well, it fixes a huge problem that used to plague AI researchers, something called the vanishing gradient. Imagine you're passing a message down a very, very long line of people. By the time it gets to the end, the message is probably weak and all garbled up, right? That's what used to happen to the learning signal in deep networks. It would just fade away. ReLU, with its super simple math, acts like a megaphone, keeping that signal loud and clear all the way through. It's what allows us to build these massive, super deep networks we have today.
But what happens when you need to choose just one thing out of a whole bunch of options? Like, is this picture a cat, a dog, a bird, or a fish? For that, you need a special tool for the final layer called Softmax. What it does is brilliant. It takes all the messy, raw outputs from the network and converts them into a clean list of probabilities that all add up to 100%. So you can clearly see, the model is 85% sure this is a dog.
And this really gets to the heart of being an AI architect. You don't just throw these things in randomly. You choose them strategically. For all those deep internal layers, the hidden layers doing the heavy lifting, ReLU is your workhorse. It's the default go-to choice. But for that very last, final layer, your choice completely depends on the problem you're trying to solve. Predicting a stock price, you'll probably use no activation at all. Picking between categories, that's a job for Softmax. Controlling a robot arm, where the actions need to be in a tight range, Tanh is perfect for that.
All right, quick recap. We have a scorecard to measure mistakes. That's the loss function. And we have the little gatekeepers making decisions. Those are the activation functions. So we have all the parts, but how does the AI actually use the score to improve? What's the engine that drives the learning?
That, my friends, is the job of the optimizer. This is the real engine of learning. Imagine your goal, that low-loss score, is at the bottom of a huge foggy valley. The optimizer is like your super advanced GPS and your hiking gear all in one. It's the algorithm that figures out which direction to step, which little knob to turn inside the network to take you one step closer to the bottom of that valley.
Okay, so how does it do that? Well, you could have the optimizer look at your entire massive dataset every single time it wants to take one tiny step. But can you imagine? If you have millions of examples, that would be painfully, ridiculously slow. So instead, we do something much smarter. We use a trick called mini batch gradient descent.
Okay, let's just pretend our whole dataset has, say, 20,000 pictures in it.
Instead of grinding through all 20,000 at once, the optimizer just grabs a small, random handful, a mini batch, of maybe 100 pictures. It gets a quick sense of the error from that little batch, makes a small course correction, and then it grabs the next 100 and does it again. It's like taking lots of small, quick peeks at the map instead of studying the whole thing for hours. It makes the entire learning process way, way faster.
And here's a little insider tip. This is where the software really meets the metal. For reasons that have to do with how computer hardware, especially GPUs, are built, it's almost always a good idea to make your batch size a power of 2. So, 32, 64, 128. It just helps the hardware process everything more efficiently, kind of like having boxes on an assembly line that are all the perfect size.
Okay, but let's throw a wrench in the works. Everything we've talked about so far assumes we have a nice, neat data set with all the right answers. But what if there are no right answers? What happens in something like reinforcement learning, where an AI is learning to play a video game just by messing around?
Right. In reinforcement learning, there's no answer key. There's no teacher telling the AI that was the right move. All it gets is a reward signal, a little +1 for a good move, a -1 for a bad one. So we, the architects, have to get creative. We have to build a loss function from scratch, one that's all about trying to maximize those future rewards.
And this leads to two totally different philosophies. On one side, you have value-based methods. These models focus on becoming really good fortune tellers. They try to predict, how good is this current situation? What's my score likely to be from here? So their loss is just about how accurate those predictions are. On the other side, you have policy-based methods. These are more direct. They don't care as much about predicting the score. Their loss function directly encourages the actions that led to good things. It's all about making good moves more likely in the future.
So there you have it. We've walked through the 3 pillars: how we measure mistakes, how the network makes its decisions, and the engine that drives the improvement.
But the real magic isn't in any one of these pieces. It's in how they work together. The loss function is the what. It defines the mission, the target we're aiming for. The activation functions are the how. They give the network the complexity and flexibility it needs to find creative solutions. And the optimizer? That's the engine, the relentless force that pushes the whole system forward, step by step, toward that goal.
So when you think about it, the most important takeaway is this. Building a powerful AI isn't just about shoveling in more data. It's an act of craftsmanship, of architecture. It's about you, the designer, picking the perfect combination of tools for the problem you're trying to solve. The real genius isn't in any one component, but in the elegant way you combine all 3. And that's it. Now you have the keys to the architect's toolbox.